All right, let's go over those problems. One of them doesn't follow the normal octet rules. And that maybe causes some problem, but that's okay. And then the rest should be doable. We'll start with sulfate, SO4 minus 2. Put the sulfur in the middle, surrounded by 4 oxygens. Abby, oxygens have how many valence electrons? Okay, so we're going to put, I'm going to put them around on the sides like this at this point. We'll move them around as we need. Brian, how many does the sulfur have? 6. Okay. Well, let's start like this. Let's make a coordinate covalent bond there, a coordinate covalent bond there, and a coordinate covalent bond there. That uses up my 6. Don't forget, we have 2 extra electrons we're going to have to use. So I'm going to just mark those out here. We'll slide those in eventually. So far it looks like things are going pretty good, except that we don't have a bond to that other oxygen. What should we do, you think? Mitchell?
Make the 2 leftover electrons coordinate covalent bond.
Slide those in there. We could perhaps do that. We said yesterday that normally we don't want those extra electrons to slide in because they're probably going to get all repelled. They probably should come to one of the outside atoms. So basically, though, you're right. What do you want to do, Abby?
Don't make them all coordinate covalent. Using the electrons on the oxygens to use the other ones.
Okay.
Fill up the empty spaces on the oxygens with the 2 electrons.
All right, we could do that. Okay, here's what we could do. There's a couple possibilities or a couple acceptable answers. We could just take this whole pair and slide it in here and make a coordinate covalent bond that way, and then take these extra 2, slide them down here. We could do that. We could do as Abby suggested. By the way, this would work, right? Everybody's got 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. All the correct electrons accounted for, and sulfur has 8, 2, 4, 6, 8. What Abby was trying to say is do this. That would work. Give one of these and one there, and then take this guy, say, slide him in here. Take one of those guys, slide him in there, and that leaves 2 unpaired. And then you take those 2 extra electrons, drop one there, and one there. There would be more than one acceptable answer here. Even what Mitchell suggested could work, although we kind of discourage you from taking those extra electrons in there. And don't forget to put big brackets around and put -2 outside. Any questions on the SO4 minus 2? I saw somebody had resonance. Do we need resonance on this? Here's where some people make a mistake. Resonance is used only if you have a double, or I suppose a triple bond that could have gone somewhere else. Some are going to say, you made a coordinate covalent bond with that guy. How do you know you shouldn't make a coordinate covalent bond with that guy? And they do resonance because the coordinate covalent bonds are moving around. Well, it's true the coordinate covalent bond could have been made with any of the oxygens, but that's not a basis for drawing resonance structures. So you only do the resonance if you have double bonds. Any questions on that? PO4 -3. Phosphorus in the center, oxygens on the periphery. Oxygens have 6 electrons. We're going to quickly show those again. Phosphorus has, Nick?
5.
5. So I'm going to start out with 1 here. As a quarter covalent bond, I'm going to put 1, 1, 1 there. I'm going to steal this guy's 1 electron, this guy's 1 electron, this guy's 1 electron, slide them in to make the bond. Now I've got these unpaired, which we're not allowed to have, but I do have 3 extra electrons, so I'm going to put 1 here, and 1 there. Giving me an octet for the phosphorus and all 4 oxygens. And I, of course, put the big brackets around. -3. Anybody on phosphate? Now's the time, of course, to ask questions. I think most of you are getting this right as I've walked around and looked at it. Some of it comes by trial and error. Okay, you got to start moving things around and see things. Hopefully you're starting to see patterns happening, things we're doing. Okay, SO3 minus 2. SO3 minus 2, S in the middle, we're going to put 3 oxygens. Just going to evenly distribute them at this time. Solomon oxygens have 6 valence electrons. Sulfur, Courtney has 6. Well, some would be tempted to say, let's go and do coordinate covalent bond, coordinate covalent bond, coordinate covalent bond. There's your 6. We have 2 extra electrons that we have to do something with. Some are going to want to put them on here. That's not very likely that those are going to go there. What's a better way to draw this, although basically that's the correct structure right there, would be to give this guy a lone pair, which is his normal situation, and have maybe make this guy a coordinate covalent, this guy have 1, this guy have 1. There's 6 black dots. Take this guy and this guy, slide them in to make bonds. I got these open spots, but I got these 2 extra electrons, 1 here, 1 there. Everybody gets their 8. Sulfur has a coordinate covalent bond, a lone pair, and 2 regular bonds. It's probably the best way to draw that. And don't forget your brackets. -2. Any questions on that one? There is some variety, as long as you have this basic structure when we're done, you're going to get the right points, you're going to get the right answer. You know, which element gets those extra electrons, or whether one of them gets both. We could argue about that a little bit. I like what I've drawn on the board. I think it's a pretty reasonable structure. Just make sure you got some colors here Thursday for the test, and then you notice a couple things. You generally give all the oxygens their electrons. If you can't make a bond, you put 1 here, you slide 1 in, and that's when you take those extra guys and drop them to make that pair. All right, now PCl5. PCl5, phosphorus in the center, 5 chlorines distributed around there. Ionic chlorines have how many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Phosphorus has, Miriam, how many valence? 5. So it would look like I need to make 5 bonds, so we should put one here, one there, and one there, and one there. So that we make 1, 2, 3, 4, and 5 bonds, giving all the chlorines there 8. But the problem is phosphorus gets 10, right? And there's no way around it. If you're going to make all the bonds, this is one of the exceptions to the rule. Generally, all the elements get 8 valence. In this case, phosphorus ends up with 10. Now, a word of caution. Every once in a while, a student will say, after they learn about that there can be exceptions to this rule, they get to the test and then everything's an exception. When things don't go well on the test and they start, oh yeah, this must be one of those that gets 10 or 12 or 15 or whatever, and they break all the rules. There are some that violate the rule. That's the exception. As it is always in life, that's the exception, not the rule. Don't govern your life by the exception. So, that has to do with the d orbitals. And he, instead of just filling up these s's and p's, he incorporates some of the d's in order that he can do this. Why they choose to do that, I don't know the answer to that, but I think we'd be content with that there can be some exceptions. And they can do it because of their d orbitals that are empty. All right, the last two. N2, nitrogen, each has 5 valence electrons, so I'm going to just put them out like this for now. I know I got to make a bond, so I know I'm going to take those single guys and make them a bond. But right now, each nitrogen only has access to 6 electrons as I have it. Right, this guy's got 6. This guy has 6. What do you recommend we do to get us to the 8, Andrea? All right, take this lone pair, and put the electrons like this, perhaps, and make a triple bond between the nitrogens with lone pairs on the ends. Everybody now has 8. That explains the stability of nitrogen in the atmosphere. Nitrogen is an N, triple bond N. And you learned about that perhaps in your biology class about the nitrogen cycle and how you have to rip these nitrogens apart. Lightning is a way to use to separate those so we can get the nitrogen fixed in a form that the plant and someone can use. Triple bond between the ends. Hydrogen cyanide, HCN. Center is carbon. Because you see here the polyatomic ion cyanide, right? So the carbon and the nitrogen have to be bonded. Then the hydrogen bonds to that. Right? Carbon has how many valence? Brady, you told me as I walked by. 4. So I'm going to just put 1 here because I know hydrogens have 1. So that's the best I can do there. Now I got 3 more left on the nitrogen. I'm going to put 2 up here for now. Put 1 there. Nitrogens have 5. I'm going to put 1 in here. Put a lone pair on top and a lone pair on the side. Hydrogen has his 2. That's good. As I have it right now, carbon has 6. And nitrogen has 6. How do I solve? Try to get them to 8, Nick.
Double by